talking about a very natural Q analog of the Eulerian polynomials. A few years ago, John Shereshian and I discovered a surprising formula for these polynomials. So I'm going to start by talking about that formula. Okay. I'm sure everyone knows that there are four basic permutation statistics that McMahon introduced at the beginning of the 20th century: the descent number, exceedance number, inversion number, and major index. The first two are known as Eulerian permutation statistics, and the second two Mahoneian permutation statistics.
Did McMahon really study the exceedance number?
Yeah. Right. So let me start with descent set, the descent statistic. So the descent set is the places in the permutation where the numbers descend. So you can see this permutation written in one-line notation. There's a descent there, and a descent there. So the descent set, position 1, position 3, and position 4. 1, 3, 4. The number of descents is 3. Then the exceedance set. These are the positions in the permutation where the entry is bigger than the position. So I make the exceedances here red. 3 is bigger than 1. 2 equals 2. 5 is bigger than position 3. So the exceedance set is 1 and 3. And x is the number of exceedances. So in this permutation, x is 2. So they're different, 3 and 2. But if we look at the distribution on the symmetric group for descents and exceedances, we see that there's 1, 0, 4 1s in both columns, 1, 2 in both columns, so descent and exceedances are equidistributed. And so these polynomials are the same, and they're called the Eulerian polynomials. And these coefficients are called the Eulerian numbers. And here's the Eulerian polynomial when n is 3. There's 1, 0, 4 1s, and 1, 2. And this formula for the exponential generating function for the Eulerian polynomials was actually first obtained by Euler. He wasn't using the definition that I gave. He was using a different definition, but this is a formula that's attributed to Euler. And this is the formula that we're going to get a Q analog of. But first we need to see how we get the Q analog of the Eulerian polynomials. So we get Q analogs by looking at the Mahoneys statistics. So the inversion number is the most basic Mahoneys statistic. And there we're just counting pairs that are in the wrong order. So inversion 3, 2, 3, 1, 2, 1, 5, 4, and 5, 1. There are 6 of them. The major index is the second most basic Mahoneys statistic, or maybe the first, because that's actually named after Major McMahon. They did the same thing everybody seems to do. Okay, so the major index is the, you sum all the descent positions. So here are the descent positions, 1, 3, and 4. We sum them, we get 8. And the distribution of these two statistics is the same. You can see that the columns, there's 1, 0, 2 1s, 2 2s, 1 3. And if we write out the polynomial, it factors very nicely. And we then see that what we end up with is a Q analog of n factorial. This is a Q analog of 3 factorial. And so Bruce talked about, and other talks talked about these Q analogs. So that's how we get Q analogs, by looking at the inversion statistic or the major index. And so what we can do with the Eulerian polynomials is combine the inversion, the Mahoneys statistics, and the Eulerian statistics in all possible ways. When we do this, we lose the equidistribution. These are not the same polynomials. They're all different. When n is bigger than or equal to 5, they become different. The first three have been extensively studied, some more than others, but all of these have been studied in the literature. And up until, I guess, when John and I started looking at this, the last one was the only one that had absolutely nothing about it in the literature. I guess no one thought there was anything interesting to say about this combination, MAG and X. So here's an example of the kind of results. Well, this is one of the very nice results that was known for inv and des, where here's the Q analog of e to the z. And this is a formula of Stanley. Okay, so now here's the formula that John and I obtained. It's another Q analog of Eulers Formula. And it's easy to see that this reduces to Eulers Formula when we replace Q by 1. So that's Eulers Formula when Q is replaced by 1, so is this. So this is the formula that we obtained. And the way we obtained this, the way we conjectured this, is we were working on something completely unrelated. We were working on Postset Topology, and we were trying to study the homology of a certain postset. I'll talk about that postset in my second talk. But so we reduced what we were doing to this formula, and we figured that this would be well known. We were at the Mittag-Leffler Institute at the time, and so we figured we would just go to the leading expert and find out where we could get a reference for this formula. So we went to Ira Gessel, and we said, give us a reference for this. And he looked at this and said, I never saw this before. And so we figured, uh-oh, this must be wrong. But then we realized, we checked it in the computer and it worked, and we realized if it's true, it's more interesting than the problem we were originally working on. So it took us about a year to prove this. So let me talk about how we proved it. What we did is we generalized it to a symmetric function identity. So the right-hand side is a specialization of this symmetric function. H of z is the sum of the complete homogeneous symmetric function, this. And we look at this quotient, and when we specialize by replacing xi by q to the I minus 1, z by that, and t by that, we get this expression. Okay, so the problem is, what belongs up here that specializes to the left side? And if we can figure that out and then prove this, we'll have this formula. So let me talk about how we obtain that question mark. So we do something a little strange. We take each exceedance and we put a bar above it. And then we have words over this ordered alphabet. And then we define the dex set of sigma to be the descent set of sigma bar using this ordered alphabet. So for example, the dex set of that permutation is the des set of that permutation. And notice there's a descent here according to the order on the alphabet. At 3, 1, there's no descent because 3 bar is less than 1. 4 to 6 bar, there is a descent because 4 is bigger than 6 bar, and so forth. So this is the descent set of that permutation, the deck set of that permutation. And it seems like a strange thing to do, but it actually has the following nice property, and that is that when we sum over all the elements of the deck set, we get the major index minus the exceedance number. So it's not such a strange thing. Okay. Next, we look at these quasi-symmetric functions. I won't define what a quasi-symmetric function is. It's enough to know what this is, this f sub t. When we have a subset of the set of numbers 1 through n minus 1, we can talk about f sub t of this, and that's defined this way. And these quasi-symmetric functions, the notion of quasi-symmetric function was introduced by Ira Gessel. So we define these Eulerian, we call them now Eulerian quasi-symmetric functions, to be the sum of the fundamental quasi-symmetric functions. For each permutation, there's a fundamental quasi-symmetric function, and we sum over all permutations with j exceedances, and that's what we're calling q and j, and we're calling those Eulerian quasi-symmetric functions. So we have, if we take for any subset T, the fundamental quasi-symmetric function, and specialize by replacing xi by q to the I minus 1, we get this formula where we're summing over the entries of T. So if we do that for decks, we get this. And if we sum over all j, and all overall permutations, we get this, because we're summing this over all permutations. And the q minus causes this to be maj minus x. So this is what we get. Okay, so now we know how to specialize what symmetric function. Oh, actually, we don't know yet that it's a symmetric function. This is a quasi-symmetric function, and we know that this quasi-symmetric function specializes to that. This is what we have to prove, and when we prove that, then we'll know that this is actually a symmetric function because the right-hand side is. So this quasi-symmetric function specializes to that. We do know that. So that's the goal, to prove this identity up here. So that's our main result, that this is equal to that. And we have an extra parameter. It works in even more generality. We can sum according to the number of fixed points of the permutation. So we get this extra parameter k, and then we sum this, and we get this. Here's where the k comes in, the extra parameter r. R is actually a parameter, not k. So this is what we prove. And as a consequence, I'm just repeating what I already said. This is the formula that follows from that. So after we wrote up a paper for the electronic research announcements, Fawada and Han obtained the following result. And their proof used many of the ingredients of our paper. But after they obtained this result, we realized that the symmetric, so they have the extra parameter des here. So we realized that this identity, this can be specialized in a different way using we use the stable principal specialization. If you use the principal specialization, a different specialization, you can obtain this. So that's why I'm calling it a corollary. And this had been done earlier when t is 1 by Gessel and Reutenauer. And they use a technique. Their technique is what our technique is based on. I'll talk about what our technique was. It's based on the technique that they used to prove this. What else did I want to say? One thing I want to mention before I get to the proof is that this expression on the right side of our formula has appeared in many places in the literature, as you can see. Some haven't appeared yet, the bottom one. This one is what we were studying to begin with, which led us to the formula. So these last two don't really count. The first one, this expression when r is 0, appeared in work, and actually t is 1, appeared in work of McMahon, and later Askey and Ismail introduced the, so McMahon was just counting multiset derangements, and then Askey and Ismail counted multiset derangement with J exceedances. I'm going to be talking about this also in my next talk. And Dang-Soo Kim and Zhang have studied this problem also. This appeared as the enumerator for words with no adjacent repeats with J descents. It appeared in work of Stanley, originating with Procesi, on the Frobenius characteristic of the representation of the symmetric group of degree 2J, on the cohomology of the toric variety associated with a Coxeter complex of type A, and it appeared in unpublished work of Gessel. I don't know what year he did this, but a numerator for certain barred words. I'll be talking more about Gessel's result in my next talk. So there's all kinds of interesting connections that haven't really been explored yet. Okay, so now let me talk a little about the proof. There are 3 basic steps to the proof. Oops, I did it again. Let me go back. Okay. Okay, so the first step is we're modifying this bijection, well-known bijection of Gessel and Reutenauer. And I'll talk about what this means, compatible pairs and ornaments. I'll talk about the first step. The second and third steps I'm not going to have time to discuss, but 3 main steps in proving this. So let me just focus on the first step, because that has some nice combinatorics in it. Now, Gessel and Reutenauer worked with necklaces and ornaments, which are multisets of necklaces. We needed to introduce a bicolored version of these necklaces. So let me say what a necklace is. A bicolored necklace is a primitive circular word on letters where there are 2 colors to each letter in the alphabet. And we have the following rule, that a blue letter has to be followed by a letter that's greater than or equal to it in value. So here's a blue letter followed clockwise by something larger. Here's a blue letter here, it's followed clockwise by something equal in value. A red letter has to be followed by something smaller in value or equal. So red, smaller. And necklaces of size 1 have to be blue. So here's 2 necklaces. Here's 2 circular arrangements that aren't necklaces, because 3, what makes this not a necklace, I forgot for a second. This is not a necklace because it's not primitive. Primitive means that if you read it, if you don't have the, any, I don't know how to describe it, that when you read it around the necklace, if you start here, you're going to get a different necklace than if you start elsewhere. So you can see 2, 3, 2, 3. If we read the necklace here, we have 2, 3, 2, 3. So this is not primitive, where this one is. So this is not a necklace. This isn't a necklace because it's red. So that's our rule for what a bicolored necklace is. In the Gesell-Reutenauer case, it just had to be primitive, a primitive circular word. Okay, an ornament is a multiset of necklaces. So here's an ornament. These three circular arrangements are necklaces. This is an ornament. We define the type of an ornament to be the sizes of the necklaces in the multiset. So this has size 5, size 4, size 4. So this is an ornament. By the way, this would not be a necklace if it were not, if it weren't for the colors, because this would not be primitive to have all 2s. Okay, the colors make it primitive. The weight of a necklace is going to be, we count the number of 2s. There are 7 2s, 1, 2, 3, 4, 5, 6, 7. So that's x2 to the 7th. Count the number of 3s, x3 to the 4th, and so forth. That's what the weight is. It tells you how many letters there are of each value. And we're going to let R, lambda j, be the set of ornaments of type lambda with j red letters. So that's what R. And this is, going back to Gesell and Reutenauer, this was their result, that if you define these quasi-symmetric functions based on a partition of n, and you sum over all permutations of a given cycle type, and you sum these fundamental quasi-symmetric functions, then this expression can be represented this way, is equal to this, where we're summing now over all monocolored ornaments of weight r. And that was their result. And they used it to count permutations of a given cycle type with a given number of descents, or given descent set. So this is our bicolored version. So now we count, remember, according to the number of, here it's according to the number of exceedances in the permutation. Here we have the dex set, and here we're counting ornaments with j red letters, and we're saying these two are equal. So let me give the bijection. It's a nice bijection that proves that those two expressions are equal. So that's what dex is. That's what the fundamental quasi-symmetric function that we're assigning to a permutation is. That's not what dex is. So this is, remember how these fundamental quasi-symmetric functions are defined. So this is what we're looking at. So for each permutation, there's a sequence. We have sequences that satisfy this relation. We'll say that the permutation and the sequence are compatible if this happens. So we start with a permutation. I'll demonstrate the bijection. We're going from permutations and compatible sequences to ornaments. That's how we prove the result. So there's a permutation. There's a compatible sequence. I took the permutation and I put the bars on top of the exceedances. And then here are the descents of the barred permutation, so we can see what the dex set is. That's where the dots are. That tells us the dex set. And this sequence is compatible. It satisfies that, because we have to have a strict descent wherever there's a descent in the permutation. So there's a descent in position 3. There's a strict descent there. There's a descent in position 6. There's a strict descent there. And notice there's a descent here, but there didn't have to be. There has to be there. So that's the sequence that's compatible with the permutation. So what we do is we write the permutation in cycle form. And then we color the letters of the permutation according to the rule that I stated before. Letters that are followed by larger letters, we color them red, and letters that are followed by smaller letters, we color them blue. So that's red, it's followed by a larger letter. 3 is followed by 1, a smaller letter, so we color it blue. So this is how we color the permutation. And then we replace the letters of the permutation by letters of the compatible sequence. So we're going to replace each I by SI, and we end up with an ornament. Replace 1 by the first letter, S1, so we get 7. Replace 4, this 4, by the fourth letter, which is in the sequence, which is 5, so we get 5 down there. So that's how we make the substitutions, and we end up with an ornament. Of course, we have to prove it's an ornament. We have to prove that these words are primitive. It's easy to see that the color rule is satisfied. We need to show that they're primitive. And we need to do a little more work than Gessel and Reutner had to do, because to show it's a bijection, Gessel and Reutner now I forgot which direction you need to prove to show it's a bijection that it's onto and 1 to 1. But if you know the size of both sets, then you only need to prove one of them. We didn't know what the size of the sets are. In the Gessel-Reutner case, that was easy to count, but in our case it wasn't. So we really had to show that it really was a bijection. We gave the inverse and to show that we had a bijection, that this really is a bijection. Okay. So that's the proof of step 1. Now I want to talk about some interesting properties that these q-Eulerian polynomials have. So let me start with a well-known property of the Eulerian polynomials, and that's symmetry and unimodality. So by symmetry, what we mean by symmetry is that the coefficients form a palindrome. 1, 4, 1. So 1 and 1 are this coefficient and this coefficient's the same. This one and this one's the same. This and this. This and this. 26 and 26, 6, 8, 6. So that's what we mean by a symmetric. So this is a little confusion. I talked about symmetric functions, and now I'm talking about symmetric polynomials, which is very different meaning. It just means that the coefficients are form a palindrome. And unimodality means that the coefficients increase and then decrease. Increase and then decrease. So it's well known that the Eulerian polynomials are symmetric in this sense and unimodal. So what about the q-Eulerian polynomials, the Mahoneys q-Eulerian polynomials? So here are the first 3, here's 3, 4, 5, and you can see, I mean, in these examples, the symmetry. It's hard to see anything about unimodality here, because of course this polynomial is less than that polynomial, and for 5 I didn't even write out what it is, what these polynomials are. But what I mean by unimodality is that this polynomial is less than that polynomial, and what that means is that the difference of the polynomials is a polynomial with positive integer coefficients, or non-negative coefficients. So if we check this on the computer, and this was unimodal, actually it turns out that one can prove this using our formula. So this is the theorem. that these polynomials are symmetric and unimodal, and as I said, it follows from our formula. Okay, so now they have this other class, we can call them, of Eulerian polynomials, where we're looking at the cycle type of the permutation. So we're summing according to cycle type, and I also included the Des statistic here. And we were able to prove that these are symmetric polynomials. Even though we don't have a formula for this, and we know very little about these polynomials, we are able to prove that they're symmetric. But here's a conjecture that we're not able to prove. I think it's hard that this is, I think it's going to be a hard thing to prove, that this is unimodal as well as symmetric in T. This is a polynomial in T. The coefficients are polynomials in Q and P. And those polynomials form a unimodal sequence. So I think this is hard. We checked it on the computer up to n equals 8, and it's, I believe it's true. Okay, so now I can lift what I've been talking about to the Eulerian quasi-symmetric functions. So recall the definitions. And so this was what I called, this top one was what I call the Eulerian quasi-symmetric functions, and this we can call the cycle type Eulerian quasi-symmetric functions. And recall the specializations that we obtain. This is what I talked about earlier. And we're able to prove all these properties for the Eulerian quasi-symmetric functions. They form a symmetric sequence, as I said before, symmetric in a different way than for symmetric function. So by sequence, we're letting the j vary, fixing the n, and it forms a symmetric sequence. Symmetric function, that follows immediately from our formula that these are symmetric functions. Even though they're defined as quasi-symmetric functions, they turn out to be symmetric. When you have a symmetric function, you can ask if it's H positive. That means when you express the symmetric function in the basis of complete homogeneous symmetric functions, what do the coefficients look like? This is saying the coefficients are all non-negative. That's what H positive means. By H unimodal, I mean that when I take the differences of the coefficients of H, the differences are positive when that's H unimodal. And P positive, that means that when you express it in the basis of power symmetric functions, all the coefficients are non-negative. So from the formula that we have for Q and J, we're able to prove all of these properties. But we don't have a formula for the cycle type Eulerian quasi-symmetric functions. So these properties become more difficult or mysterious. So let's see what we are able to prove in that situation. We're able to show that we get a symmetric sequence. We're able to show that we have a symmetric function. We prove this by looking at the ornament characterization of the cycle type Eulerian quasi-symmetric functions. That's how we get that it's a symmetric function. And what about H positive? Well, here I've expanded. I don't see the light. It's not showing anymore, is it? So here I've expanded this. By the parentheses around the 6, I mean cycle type, a single 6. So we're looking at cycles here. So when I expand that, you see the minus sign in the homogeneous symmetric functions. So it is not H positive. But it turns out that it is sure positive. Well, checking on the computer was sure positive. We checked this up to n equals 8, I believe, and it turned out that we got sure positive every time. So we're conjecturing that these are sure positive, and the symmetric sequence is sure unimodal. That sequence is sure unimodal. In other words, when we take the difference of q lambda j minus q lambda j minus 1, we get a sure positive function, a symmetric function. So I think that's an interesting conjecture. It would be very nice to understand why these things are sure positive. Are they Frobenius characteristics of some representation? That would be interesting to know. What are these things? But I think this is an interesting class of symmetric functions. I think these are hard problems. Okay, so I've added sure positive and sure unimodal with question marks. And now what about p positive? So Shureshian and I conjectured by checking on the computer that these are p positive. And recently, in a joint paper, we're able to show that they are p positive with Bruce Sagan, and we give explicit coefficients in the p-basis expansion of these quasi-symmetric functions. I won't say what they are. I'm speaking at the meeting in San Francisco, so I will be talking about this there, what these coefficients are. But what's very interesting about this is we're able to use those coefficients to obtain a cyclic sieving result. And so let me say what that result is. When you replace, so this goes back to Bruce's talk, when you replace Q by the root of unity, primitive root of unity, you get a polynomial in T with positive integer coefficients, which I think is interesting in itself, that you get integer coefficients when you replace it with a complex number. But it's counting something, and what it counts is a very natural group action. It's counting the number of fixed points when you conjugate with this permutation, this cycle raised to the power n over d. You conjugate, and the number of fixed points. So you conjugate the permutations in this set by that permutation, and the number of fixed points of that action is equal to the coefficient of t to the j in there. And this proof relies on symmetric function theory, so it's an interesting bit of combinatorics. Okay, so let me close by talking about some related work, just mentioning it actually. Fawad and Han got a type B analog of the Eulerian polynomial formula, and their formula, which specializes to our formula, type B analog of that. And they also look at Q analog of Euler numbers in another paper. So they have two papers, two follow-up papers. My student, Matt Hyatt, has a type B analog of our Eulerian quasi-symmetric functions. And he's got some interesting results on those. And recently, Shureshian and I found a connection with Stanley's chromatic symmetric function. And this connection involves chromatic quasi-symmetric functions, which I don't have time to talk about. Actually, I would have had time. I see my talk. There's nothing left. I'm clicking, that's it. So I finished early, which I hope you don't mind. Thank you.
So questions?